You can do it too, believe me. If you can learn CSS, I often say this, you can learn assembly because boy is assembly simpler, right? I still couldn't tell you all the stuff in CSS, and I have done a bunch of work with it. Assembly, I didn't have to do very long, and I can just tell you it's because it's much simpler. It's very well specified.
Hey folks, and welcome to Marco Code. We're going to be working on the 1 billion row challenge. It is going to be episode number 4. And today is the episode I think that I suspect Casey has been waiting for all along, because we're going to be looking at assembly code. Casey, welcome.
Hey Marco, thanks for having me.
Just to tell people again, just as a quick summary of what we did last time, we worked through the 1 billion row challenge. We added some code to essentially find semicolons and find new line characters in lines. And we found out it's going to, just the addition of these two find calls adds an additional 10 seconds or so of execution time. And then you gave me as homework, essentially, hey, let's have a look at the assembly code. Let's have a look at what is actually going on there under the hood. And this is what I did. And for you and the viewers, you're probably going to learn more about Java and assembly code than you probably would have liked to know. Well,
yes. Let me jump in right there, actually, before you talk about how you actually got the assembly language code. I'd like to sort of just tell people briefly why we care, right? And so I think there's a lot of misconceptions around assembly language code that largely stem, I think, from sort of older programming practices, where in the old days, you really kind of did need to write assembly language code yourself a lot for performance. If you're talking about the 70s and the 80s, 60s, 70s, 80s, and even 90s, you were often writing important things in assembly language because computers like CPUs simply weren't fast enough and weren't sophisticated enough, and neither were compilers, to generate things that would run at the kind of speeds that we needed to. But nowadays, compilers are very sophisticated, and computers are very sophisticated themselves at executing the code that you send them. And so we don't really have to hand roll assembly language, hardly ever. There are some, I don't want to say never, but it's very rare. Even for people who care a lot about performance, it's not that common to do. But those of us who care about performance always do read the assembly language. And so what hasn't really died is the need to look at what the assembly language is. And the reason that we care so much about that is it's the only way for us to really know what we're asking the CPU to actually do. Because everything else is just a high-level language construct that, as far as we know, could turn into anything, literally anything. Because in between that high-level language code and what the computer is actually going to do is a whole chain of software that not only could be generating inefficient things to hand to the CPU, but it could be generating buggy things. Right? It could actually be generating errors. And in fact, there was a recent Cloudflare post about this where there was a bug in the Go compiler, right, that was causing it. So looking at the assembly language is an absolutely critical skill for people out there who want to do performance work, security work, robustness work, all of that stuff. It's so important. And so I try to expose people to as much as possible to say, look, it's not that hard to learn to read this stuff. You don't have to learn to write it. And it's a perfect way for us to sort of get a feel for what's actually going on. And so since we're doing this 1 billion row challenge, there's a couple different reasons that I wanted it here. The biggest one is just so we can verify what's actually going on, just to see, so we know, is the compiler removing something? Even during just our timing, if we want to remove a little bit, how much optimization did it do around that? Did it remove this routine entirely so we're timing nothing? Just so we can kind of know roughly what's going on. And then the other big one is, as we start to optimize this challenge, we may get into situations where we need to know, what is the JIT doing here? It seems like it's taking too long. Why is it taking too long? The code it's generating is taking too long. Why is that happening? And when we look at the assembly, we can go, oh, I see. It's because it's doing this. And that gives us a way to think about how we might convince it not to do that. So that's why we're doing this. Marco, how did you get the assembly for us here?
That's why we're doing
I'm
it,
interested
right?
To know. Yeah.
Yes. A bit of background knowledge for everyone who programs Java. So by default, when you have your JVM, you actually cannot just get the assembly output. What you'll need to do is you'll need to build something which is called the hotspot disassembler. It is a tiny library at the end of the day you have to put into your JVM directory, and then it all works. But the thing is, it's operating system dependent, obviously. It's a bit finicky to get it, actually to build properly. So you're going to spend some time. But the article you see here on the Oracle homepage is actually a good start to get into how to build hotspot disassembler and how to get started with it, actually, if you want to do it in your free time, so to speak. So that is one thing. You need a JVM, which we obviously have. You need the hotspot disassembler library, which is essentially just one file, and then you're good to go, and you can enable disassembly of what the JIT does. Which brings us actually to the second topic. And this is maybe a bit about how actually Java programs run in general, JIT versus AOT versus how many JIT compilers there are, so on and so forth. So at the end of the day, essentially, what modern Java systems have is a process which is called tiered compilation. So first, when you start your Java application, then you run in interpreted mode, meaning the bytecode you have compiled previously will just be interpreted relatively slow, so to speak, but there is no native code yet. And then you have two JIT compilers in the JVM world, C1 and C2 compiler, which people who used Java maybe 15 years ago might still know as the client JIT compiler and the server JIT compiler. Why was that? Because back in the day, you said, well, the C1 compiler actually is a bit quicker and a bit faster, doesn't do really full sophisticated profiling, and you would use it for desktop software, for example, where speed kind of matters. Whereas the C2 compiler, which is a bit slower but produces more optimized code at the end of the day, would have been more useful, on the server side of things. That was the case until I think Java 8 or so, and with Java 9, effectively, we have a process for tiered compilation, which means interpreter code, we have C1 and C2 compiler working in unison together, which means your code will go through different stages. It will start off interpreted mode, then the C1 compiler will happen, then there will be a bit of C1 compilation with profiling, basic profiling, full profiling, and then you have the C2 compiler with all the previously collected profiling information. So your code will actually go through various stages, and it can be compiled or recompiled, decompiled a couple of times during the entire process. Casey, was that explanation kind of sufficient?
Yes, and like I said, this is one of the things that I was really interested in when doing the stream with you, because I don't work with Java, and I am very interested to learn sort of what that underlying infrastructure looks like. I do have a question for you already, which is that and maybe this will have to be for next time if it's like something you got to go poke at the JVM for. But
I probably do.
Yeah. I was wondering as well. So when you're talking about compilers like this that are doing sort of JIT, oftentimes they do what we would call profile guided optimization, meaning they're watching. And I saw, as you're going to show it here, there you kind of gave me like a dump. You're like, hey, is this sufficient? I was like, yes, that's great. Right. Included in that was actually a little bit of markup where it's like, we looked at how many times each of these branches were taken, right? Like I was looking at things like that.
Yes.
And so what I was wondering is, does this infrastructure sort of persist that data at all? Meaning, when you're running this program, if you've run it, millions of times before, and then you close it down, you're going to run it again. Does it load up state from old runs of the program so that it can start with that? Or is it only using just the profile information that it's had so far on the current run? I was curious about that.
To my understanding, it's only so far on the current run.
Okay.
There are some, developments with AOT compilation where actually you can do some profiling runs and then save that profiling information and use it later on. But so far, it's not persisted between runs. I mean, with the JIT, the default behavior, it's just, for the time it's running, essentially.
I see. So it runs the program for a little bit.
Yes.
Then interrupts it and uses whatever it got in that little bit and says, that's what I'm going to use for my profile guided JIT of this area, or
pretty much. I don't even think it interrupts it. It just happens in parallel, so to speak. So we just,
it swaps it in, I should say.
It swaps it in, yes. But essentially, that's it. Yeah, we just run interpreter mode. We count invocations. There are certain thresholds when the compiler notices, hey, that method is being called. I mean, the thresholds, you can actually look them up online. 1,000 times, 2,000 times, whatever. Then this is a hot spot. That's why a hotspot compiler.
Understood.
And then we compile into native code and so on and so forth. And actually, that discussion brings us to maybe these two lines you can see here.
Yes.
Because there are effectively, if you want to control this entire behavior, there are roughly, I kid you not, 1,000 flags
Wow.
you could use in different combinations and whatsoever. And I just want to briefly show you what I came up with here, and explain you what's going on. So you control the entire behavior of the JVM with these XX options you can pass in at program startup. And I thought I want to do two things. The first one is I just want to do a very normal JIT-based run, which means, again, as I said, we start up interpreted mode. We have C1, C2 compiler. It will actually go through the entire cycle. I'm not going to change any thresholds, which you also can do. So it's just a normal run with the debug information. And just for the Java developers out there, if you're listening, you have to have these unlock diagnostic VM options here enabled. This is actually the entry hole into these advanced options. And then forget all these additional debug save points for now. The only interesting thing about what I wanted to show you is we were essentially interested in the assembly of, let's say, one method. We could print out all the assembly that JVM does for, the entire class, for all the helping classes, whatever. I actually only wanted to see for the find method what the assembly is going to look like. So This is actually it. This will run the entire normal process and just print out the assembly for the find method itself. Right. And not only that, by the way, because the JVM with these debug options, it will actually give you a hotspot log file. And the hotspot log file tells you when was this method compiled, how long did it take, how long did the compilation take, was it inlined, was it not inlined? And there's literally a huge XML file of debug information you can have a look at later on. So that's where these other options are essentially for.
And I assume that basically, what we're looking at here, like we want the disassembly because we're interested in what it did for our particular code, but I'm guessing that most of these features, including that one probably, are targeted towards JVM developers who are like working on the JIT and trying to debug, like, why did that function not get compiled, or why is it slow? So they probably care a lot more than we do about, like, specifically when did you decide to JIT this thing and why was it done in this way? So we don't need a lot of this data, but it's kind of cool that it exists because, more data is always better to have if you can get it, right?
Then I thought, well, we have the normal, what I would call fully tiered application run, and I thought, well, the thing is, when I think about it, our find method doesn't really do too much crazy stuff. So there is not going to be dead code or whatever. There's not much to optimize. So I thought, just out of interest, hey, what happens if we do this run and we have two basically changes? First of all, we disable tiered compilation, which means actually this flag means get rid of the C1 compiler, just jump straight to the C2 compiler to the very last stage, no tiered compilation in between. The second one is compile threshold 1 means as soon as a method has been called one time in an interpretation mode, we actually start the C2 compilation straight away. And I'm not saying that these two parameters are the best way of doing this, but I just wanted to see what happens. I wanted to find out, hey, does the assembly code which is going to be produced going to be much different than the fully tiered run whatsoever? But this is what I came up with. And as I said, you can essentially configure these thingies any way you like.
Got it.
All right. So I did that. I'm not going to run it because I just ran the program before, so we can save, the 10, 20 seconds or whatever. And you'll find there are two text files here, which contain the output. The assembly,
named after me, which I appreciate. It's like I am the
yes.
I am the namesake.
Yeah, you're the namesake.
The titular Casey is here to talk about Casey.txt.
Okay, yeah, Casey's here so Casey is going to do some blah and talk about Casey.txt. Right.
There you go. Yeah.
So we've got Casey fully tiered. We've got Casey tiered disabled. Let me jump into Casey fully tiered. And these other flags, unfortunately, give us a bit of debug information we can actually get rid of, but we don't actually need. But the interesting thing is, when we go to the very bottom, we will see one thing. Mm-hmm. We will see we have the find method. The one we wanted to see. We can see the bytecode for the find method down here. Yes. This is actually JVM bytecode. And we also see how often that method was invoked through the interpreter, which is roughly 400,000 times, right? So this is just some information we got. Now,
Can I ask you a quick question about this? Just because I don't know anything about Java bytecode. I noticed this at the bottom of the file, but I was like, well, I'm not. So it's kind of, I mean, like I looked at it, I was like, okay, I could kind of see, it's sort of, the names are sort of self-explanatory, so it's doing, I was curious, what are the numbers before each one? Is that like its location in the stream? Because I noticed they aren't sequential. Like it goes from 7 to 10 directly, for example. So is this some kind of, like what does those numbers indicate exactly? I had some guesses, but I wasn't sure.
I'll need to get back to you on this.
Okay. Next time. It's not important for what we're doing now at all, but I was just, it was one of those things I was like curious. I was like, okay, I've never seen one of these before. Again, I don't work with Java. And I was like, I was curious. What are these numbers here?
Yeah, right. And then what you can do is some sort of a, let's see, compiled. If I'm actually compiled, if I can start writing today. Right. So when you search for compiled in the file, I'm just going to briefly show you something. So we found 3 invocations. We can see that the method was compiled, the find method was compiled, and it's a C1 compiled method. So this was when the first JIT compiler, the C1 compiler, actually compiled the method. Then if we hit enter once more, we can see, hey, the method find was again recompiled, this time by a C2 compiler, right? And then if we hit, compiled once more, we'll see that here is the third time compiled method, right? What is compiled, right? Okay, once, twice, 3 times. So we actually have the method being compiled 3 times. And if I showed you the JIT watch program, which I'm also, hopefully we can get into it in this stream and maybe, next time then.
It's probably going to be next time, but yeah.
Next time, yeah. Then you can actually see when these compilations happened, how long they took, and you can see a nice timeline, all of that. But in any case, in the scope of the fully tiered program run, we have 3 compilations, 1 C1 and 2 C2 compilations. Then let's have a look at the Casey tiered disabled file. And when I go down here to the find method to our bytecode, I can see that the interpreter invocation count is not even 10,000 times. And that's because we set, the invocation count to 1, the limit, and said, hey, please stop, interpreting, compile straight away. This is actually what's expected. So, I mean, just 10,000 invocation counts here. But because we disabled tiered compilation, we would expect to not find, and actually this is it. There's just one occurrence here. We just see from the C2 compiler, we just see 1 compilation to our assembly code. I don't even know, by the way, if I just showed you the assembly code before, but here we go. This is the assembly code of, actually, there's quite a few lines of assembly code here for our find method. When you compare them, and this is just one last thing, and then I'll shut up. And my hope is just to now give it over to you, and then I'll just listen for the rest of the hour.
Gotcha.
Just by briefly looking at it, when you have a look at the lines that are being compiled here, and let me just briefly go to Casey fully tiered with a visual overview, so to speak. It is much, much shorter, actually, with the fully tiered version, if I'm not mistaken. At least it looked like much, much shorter to me. It actually is. Yeah. So here you pay. Yeah. So this is my very basic first look at the assembly code without even having a look at the individual lines.
I guess I'll start with a couple things.
Yes.
First of all, thank you very much for doing all that. You can kind of see also some people may, if you come exclusively from the Java world, you may now have a little bit of a feeling for why people like me are often like uncomfortable using languages like Java, right? Is because if you imagine being in a position where when you're programming, you usually like to know, for example, exactly what is being executed, having to go through all these steps isn't great. And that may be one of the reasons why, as we'll see, maybe in next episode, we'll talk about JIT Watch. I'm assuming that's why some people started making things like JIT Watch, is because they were people like me who wanted to always know this stuff, and they're like, I don't want to go through these steps every time, right?
Yeah.
So in my world, when we're running something, when we step through it in a debugger, we just have the disassembly. So it's just there always for us, and it's never a big deal. And so that's one of the reasons why, like, I always like a development environment where it's trivial for me to see the assembly, because I learn a lot about what the compiler is doing with my code and what's going on that way. So what I wanted to do first was say, okay, anyone out there who looks at that big thing that you scrolled through, because I think it would also help at this point, Mark, if you could show the function again for people, the actual source function that we're talking about here. It's very short, right? It's very short.
Here we go.
There it is. Right?
This is it.
So you look at something like that, it's literally just a loop, right? It's just a simple for I loop that goes from I to BB length -1, right? And all it does is say, is this, I assume these characters are 8 bits. I don't know exactly what you're testing, but I assume they're 8 bits based on the disassembly. So testing 2 8-bit characters, standard character encoding, 8-bit characters against each other, and to see whether or not they're equal. That's it, right? And so you look at that, and it generates all this assembly language code, right? So I can totally understand why somebody out there would be like, oh my God, like, these people, like, they must be these wizards from the FFmpeg team. I'm never going to be able to read any of that. I have no idea what's going on. I give up, right? And I can totally understand that. So I wanted to start, before we do anything else, by showing why that is not necessary. You do not have to have that reaction. So I sent you a little link that I was hoping you could bring up on screen.
You did. Here we go. Here we go.
And this is with a tool that I think I've mentioned on the stream before, and it's an absolutely fantastic tool for learning assembly language. If
I have to interrupt you briefly. So I have a friend who's also into performance work in Java, actually, and he's been following you for quite a while. And he saw the first 2 episodes, and he literally sent me, "Hey, Marco, it's going to be like it's going to take Casey probably 30 more minutes to mention Godbold's Compiler Explorer."
Yes. And
then you just said it. You sent me, I think even on the same day, he sent me the email, you wrote me that, and I was just happy because it all just worked out. Yeah. So here we go. Godbold's Compiler Explorer.
Your friend is 100% right. It's in fact, if I'm upset that it took me 30 minutes, like I try to get it in as soon as I can. And the reason this is such a fantastic tool is because it is designed to shorten that gap that we just talked about, where you had to do all this work and install this thing in the JVM or have Git, where it's a website anyone can go to. They just type into their browser and there it is. And it allows you to type in source code on one side in a variety of languages and see the assembly update, instantly is not the right term, but in interactive rates, right? On the other side. So it's very easy for you to learn how assembly works because you can do your own little experiments. Like, what happens if I change this to a less than sign? And you can see exactly what happens to the assembly. It's like, oh, that's so much easier than any other way, because now you can use a language like C++ or something, and see the disassembly change before your eyes and go, oh, that's what it's doing when I change these things. So what I wanted to show here really quickly was the reason that people like me don't get scared when they see that giant dump of disassembly that you showed in the Java side is because we've sort of learned from, experience. We've learned on much simpler things, And now we kind of know what to look for, so we can more quickly parse these giant things. Right. We didn't start there. Like, we didn't start by looking at that giant thing and be like, what the heck is going on, right? We started small, and very quickly you just kind of build up, like, oh, okay, because assembly language is very simple. By definition, it's the simplest thing that you can tell a computer because that's what the computer operates on. So it's very simple. It's things like add these two numbers together is all it can really do. It doesn't have a huge host of things like, there's no hash table built in, right, that it can do in assembly language, right? So if you look at what I've done here is I created a copy of the function that you had. I tried to copy it almost verbatim, and there's only a few slight changes to it. What I did was I made it so that in C or C++, you could really compile this with either, I did it so that it would recreate effectively what the JVM is having to create code for. Now you can see at the top, I've introduced a thing called struct array, right? This is just like a bundle of data. It's like a class or whatever you would think of in Java that has some data members, right? And this is just from me reverse engineering the assembly language you sent me. So you sent me that assembly language, I read it, and I was like, oh, I see how it's accessing memory here. I'm going to create something that I think roughly captures what Java must use as its in-memory format for an array. And what I saw was that it looked like it was a integer length, meaning it was a 32-bit length field, followed by the data. And those were not at the start of memory that contained the array. There was 12 bytes of other stuff. And I'm assuming that's some like stuff that's included there, like, oh, this is an array, or some garbage collection information, or who knows what. But it's not. So I put ignored A, B, and C there for my 12 bytes. Right. Does that make sense?
Yeah, it does make. I was wondering what these are. Okay. Yeah.
Yes.
Cool. Yeah.
And that's because I wanted everything to line up. So in other words, that struct that I put there is basically just a dummy memory layout that mirrors what I saw the JVM creating disassembly for, roughly. I didn't spend much time on it. I just kind of looked at it a little bit because I wanted to make sure I could show you something on the screen that'd be useful. So I spent enough time looking at it so I would know, like, okay, here you go.
Right.
So this is a find implemented in C that is basically the same as what the JVM is trying to generate code for. And you'll notice there's the change of, I had to create the array myself because that's built in Java. But the only other change really is there's an integer secret first parameter that's an integer. And I put that in there because looking at the way that Java was generating JVM code, it looked like it had some kind of a parameter that was being passed into this function that was not a parameter you had specified. So maybe that's something that the JVM is just doing, like some kind of pointer that silently gets passed, you know, that kind of thing. So I was just making it line up with what the JVM's doing. And I'm sure someone who is very familiar with JVM could tell you exactly what that was. They'd be like, oh, yes, it does it this way. But, you know, like I said, I don't work with Java, so I'm just going off the disassembly that you sent me and nothing else. So if you take a look at what this is, that's all it is. I've done one thing, which is I got rid of your throw at the bottom just quickly, but I do have a throw in there, and we can switch that on. So we're just returning always. And on the right, you can see the disassembly that we actually got for this function, and you can see it's much, much shorter, right?
Only 19 lines. How dare you? How dare you? Yeah, right.
And if you take a look at this, we can sort of zero in on the part that we actually care about, and we can talk about those relative to each other. So whenever we call a function in assembly language, there's some things that we have to do at the outset potentially that don't really have to do with the main work that the function's going to do. So these are things like preparing some parameters, loading some stuff in that we need, that kind of stuff. And that happens throughout the code base, right? Like, for example, in this case, we have coming into this, we've got an array that we're working with. Maybe we need to sort of like get some information about that array, that sort of thing. And this is all stuff that we won't go into in detail because, again, like, you know, I'm not giving a whole class assembly language. Plug for my course. If you want to learn this, this is what I teach. So you can go to computerenhanced.com and you can learn this stuff if you want to. But I'm just giving the brief version. Yeah, I'm just giving the brief version here. So the part that we're actually the most concerned about, just from a perspective standpoint, is we're concerned about the loop. right? That's the thing that's going to run over and over and over again. So when we're looking at performance, we tend to look at a couple different things, but one of the biggest ones is where are we spending all of our time? And we're typically going to spend a lot of our time in loops, in things that do happen repeatedly, because computers are so fast nowadays that if something isn't done multiple times or doesn't have a loop in it where it's doing something multiple times, it's probably not going to show up very large on our profile. It's not going to affect our runtime that much. And so the way we can read this code, and again, Compiler Explorer is just really handy here. If you notice, if you mouse over, let's say, the body of that loop, the if bb data account thing, it will actually show you on the other side. It will highlight, like move on and off of it with your mouse cursor. It'll highlight the code for you, right? It's very nice. It shows you where everything was coming from. Now, because this is an optimized build, you can actually see up in the corner there I have a -03 in the ARM V8 A-clan thing, right? I'm telling, hey, optimize this stuff. That does make disassembly harder to read because it's going to do more crazy stuff to our code, right? But even so, what we can do is we can see how this code is actually working, and we can understand which part is the actual loop. Now, what you'll see is when you look at ARM disassembly, and I don't read ARM assembly, by the way. So I'm kind of like, this is not my home turf. I'm an x64 guy.
Mine either.
Yeah. I'm an x64 guy, but you know, assembly languages are very similar. If you know one, you kind of know them all. You just have to like look up some things, a couple mnemonics, like exactly how does this thing work and so on. What you can see over there is the assembly language listing basically consists of a instruction name, an opcode as we'd call it, which just tells the CPU what it's going to do. And those are the little mnemonics like LDRB, CMP, B.EQ, right? Those are just shorthand for what it does. In Godbolt, you mouse over it like you just did, it shows you what it is. It literally, like this is why it's such a great learning tool. It literally shows you this is what the CPU will be told to do.
And shout out to JIT Watch because it comes pretty close to this, but we'll see next time. Yeah.
JIT Watch is probably the compiler explorer for Java, right? It's what you would use.
Yeah, pretty much. Yeah.
And then on the other side of the instruction, it's got what the operands, like what it's going to actually do that instruction to. And the CPU uses things called register names for this. It basically says like, okay, I've got these sort of, you can think of them as temporary variables are the best way to think of them. In the old days, they literally meant storage. In the old days, like way back, like we're talking 30, 40 years back, they meant literal they were literal things like inside the core of the CPU that were storage. It doesn't work that way anymore. So that's kind of like an old way of thinking about it. So really nowadays, the best way to think of them is temporary variables. That's what they are. And these instructions, basically, these opcodes that at the beginning, the operands that are going to be fed to the CPU to do it, it gives them like temporary variable names to say like where I want the result to be placed or where I wanted to get the input from. And basically the only thing the CPU really has the capability to do is to move something from memory into one of those temporary variable names, to move something from one of the temporary variable names back out to memory, and then a bunch of instructions that can modify those things, right?
Yep.
That's all it's actually able to do with our data. The rest of the things that are in those opcodes are either special purpose things or flow control. Being able to do things like, okay, jump to a new part of the program, right? And so when we're talking about a loop, what that will look like in the disassembly is it will look like a label, and you can see it there, LBB0_2, right? That's a label. That's just marking a place that we might talk about. It's not an instruction, doesn't do anything. It's just a little markup in the assembly that says, hey, here's where something was jumping to. And then in ARM, there's this B, right, is the instruction, B dot something. That stands for branch. When we see B dot something, it will have a label. That label will tell us where we are going to go if the branch happens, right?
Right.
So we can read this loop actually just with that knowledge. We can see B.EQ means branch on equal. B.NE means branch on not equal.
Not equal, yeah.
Right? You can hover over them if you want to know what they are. And again, I apologize if I'm saying any of that indelicately. Like I said, I don't read ARM disassembly. So there's a real ARM assembly expert would probably say, look, well, it's not really not equal. It's, it's like, but anyway, those are what are controlling our loop, and we can see exactly where it goes. So we can see that it's jumping back up to LBB02. It's doing two things we don't know, an LDRB and a comp. We'll talk about in a second. Then it's doing a branch if equal. That's our check to see if our character is the same. Then we're doing an add, a comp, and a branch not equal. That's our loop condition to see that we're going to the top. So that's it. 6 assembly instructions is all we have, right? And so when you think, oh my God, I could never understand how this would work, it's like, actually, if you can understand these 6 instructions, you know exactly what your CPU is going to do for this loop. And guess what? The loop itself in C is 5 lines of code, right?
It is.
You see where I'm going with this, Marco?
It is. Yeah. I do see it. Yep.
Okay, so let me briefly tell you what these instructions are. We won't belabor it. Like I said,
sure.
You're welcome to take my course. I will never complain about science if you want more info, but I don't want to go too in-depth on something we don't really care about that much in the course of this thing, because we're not going to be micro-optimizing at this level since the JVM is the thing that's producing the code. There's only so much we can do. So we're just trying to read it and know roughly if the JVM is doing the right thing. So the LDRB, that is the thing that is pulling in the new character. That's basically a load. And it's loading off of the pointer to the array data. That's how that's working.
Guess what CMP does?
Guess what CMP does? The way that things work in assembly language usually, and CPUs I should say, is you have these comparison operations. Also, regular arithmetic operations also do these oftentimes, so you can actually do arithmetic and get comparison for free. What they do is they set flags. So when you do a CMP, what it does is it does like a subtract usually, for example. It'll just subtract the 2 numbers. And then it sets some flags. Was the result 0? Was the result negative, right? And so by doing a subtraction, if we subtract 2 numbers and we say, is the result 0? Well, if it was, they were equal, right? So we can do it, now we could do a branch on whether that equal flag was set. Let's say it was negative. Well, now we know that one was less than the other one. Let's say it wasn't negative. Now the one was positive, right? So the way that these things work at the CPU level is you just typically have one arithmetic operation like subtract that sets some flags, and then your branch operations branch on the flag, right? And so branch b.eq means branch on that 0 flag, for example. If the flag is 0, we're going to branch. Or if it's not 0, we're going to branch, right? And so that comparison, that's how that works. It's going to do the subtract. It's going to branch on equal, because if it was equal, we found our character. We jump to LBB0, which 5, which is the end of the function, and we exit, right? We found it, right? Now, on the other hand, if we didn't find it, what do we need to do? Well, we need to do an add to do what? Count plus, right? We're just moving forward by 1. Then what do we need to do? We need to check if we hit the end. Same instruction. Comp again. This time we want to branch when we didn't hit 0, right? When we didn't get to the same value that we were expecting.
Right, and execute again and again and again and again.
There you go.
Right.
That's it. Assembly language, not so complicated. Right?
not so complicated. No, not at all.
So, now, there's one thing I'll point out before we leave this, because that was all I wanted to show. I just want to show, like, it's not scary, right? It really isn't. It's very easy to learn to read this stuff, and once you do, boy, do you gain a lot of power, because now you can know exactly what's going on, and you end up being one of those people, like, if you read those blog posts where, like, how did they reverse engineer this? It's like, this is how. They learned that, and it's not that hard, and they just spent some time applying it. That's really all it is. So you can do it too, believe me. If you can learn CSS, I often say this, you can learn assembly, because boy, is assembly simpler, right? I still couldn't tell you all the stuff in CSS, and I have done a bunch of work with it. Assembly, I didn't have to do very long, and I can just tell you it's because it's much simpler. It's very well specified.
That's the best comparison I've heard in a while. Okay, right.
So don't be scared of assembly. Don't be scared of assembly. You can learn it, believe me. So anyway, so that's all I want to talk about there. I just want to mention one thing before we go on. When we have a function call, right, we don't think very hard about that in higher level languages, because that's sort of one of the primary things that a higher level language does, is we just type in a prototype and we don't think about it beyond that. It does type checking for us. It sets up the function call stacks and all that. So we don't do any of that work in the high-level language. Down at the CPU level, those things don't really exist. There are some things like call instructions that sort of facilitate them, but it has to do all the work of like figuring out like how do you pass a parameter in the first place, because there is no such thing as a parameter in assembly language to a function. Well, the way they do it is by conventions. So what happens is when we call a function, those temporary variable names I was talking about, those register names, what happens is there's a convention for how you stuff those things full of your parameters. So for example, on ARM, maybe it's like W0 holds the first one, or X0, W1, W2, W3. We put the first, second, third parameters in there, right? And so what I wanted to point out is that in our particular thing, the character that you're searching for is being passed in the third register, which is either W3 or X3, depending on how I think about it. The W and X prefix you can see on the side we're talking about registers is how wide you want to talk about the register. If you want to talk about all 64 bits of the value, it's X. If you want to talk about just 32 bits, it's W. So they're the same register, they're just different widths of it. So I just wanted to point out, because I'm going to do a little trick when we go back to the disassembly and just say, like, so what I was able to do that trick with is because I know or figured out from just looking at the disassembly that the third register is the one that's holding that character, and I knew that it had to be either the second or third, depending on how Java was doing its convention. That gave me a little way of reading the disassembly faster, which we'll see in a second. So that's, hopefully everyone roughly gets this, not in any detail at all, but just can kind of see, like, that's where I'm coming from. I'm used to looking at things like this. They're very short, actually, in languages like C and C++. Yeah. I would also say, before we leave, change that if 0 to an if 1, so we get the throw instead of the return. And then watch what happens to the other side. See how we added some cruft, right?
Right. Mm-hmm.
Just because we're going to see this on the Java side, once you start having things like thrown exceptions, you add complexity to your thing. Like the more, like as soon as you talk about, there's going to be exceptions thrown, you add more code. Oftentimes, and you can see here, as much code as the function itself will oftentimes be thrown in there as stuff that has to handle things like exceptions or balance checking or any of those other things.
We're still at plus 10 lines as opposed to like the plus 300 lines we're going to see in a second. But yeah.
So now, just to close off this episode, let's go back, and because we don't have that much time left, let's go back to our Java disassembly here. And what I want to show you, I think, will probably surprise some people.
Which one do you want to see? Do you want to see the fully tiered, last, fully optimized version? Or
it's
which
really,
one?
Your fully optimized is fine. It really doesn't matter, but fully optimized is fine.
Then let's have a look at, let's see, compiled method. Here we go. Okay. Yep.
Okay. So we start at the top, and what this is going to be doing here, and we're not going to go through it, like I said, is doing a bunch of that setup, and the setup is like more complicated again because I assume. So one of the problems that I have with reading this disassembly is I also don't really know all the requirements of the JVM, so I can't always say for sure whether it created something sensible or not sensible. So I'm not really going to critique the code one way or the other. But what I will point out is when we enter this function, right, we would expect to see, and I guess I don't know if I checked this one specifically, so we'll see if this doesn't happen, we'll bounce over to the other one, but we would expect to see in that third register the character that we're going to actually be comparing against. So let's just try skipping some of those people. Take a search for W3 in here, for example. Okay. So if you take a look at this, we can see here there's an actual comp for W3, right? It's actually happening there. That's comparing against something that it did load. Let's look to see how if we got any other comparisons to W3.
Yeah, sure. Let's see. We've got one here.
And so let's stop right there. Take a look at this. What does this look like? We've got a.
It looks exactly like what we had early on. Yeah.
Grab the whole thing from LDRSB down to BLT. Just highlight that.
Yep.
So what do we have here? Well, we've got 6 instructions.
Yep.
Just like we had before.
Yep.
We've got a load, followed by a compare, followed by a branch equals, followed by an add, followed by a comp, and the only real change here is that it's choosing to do the branch using b.lt, which is just a different mnemonic. Right. So the branch you can actually read too, like go back up there, to the code, you see that go down a little bit to the bottom of it, to just the b.lt. You can see that it's branching. We don't have labels in this disassembly, but that's just the address it's branching to. You can go find that address, go up a little bit to where that address actually is. You don't want to do that search exactly. Just you want to just look at yourself. There it is.
Yeah.
Right.
There we go. Yep. I think so. Yes.
So this really isn't doing much else that the C version wasn't. So now I'm both happy and unhappy when I see this. And this is where I'm going to set us up for next week, right?
Right.
Where maybe we'll look at JIT or maybe we won't, depending on exactly what we're doing. We'll look at JIT eventually. But why am I happy first? I'm happy because the JVM did not produce grotesque code for this loop. This is what I would expect to see, right? Now, there's a number of things we could complain about, such as the fact that it's not going wide and all these other sorts of things. So we could nitpick, but given that we didn't give it any help, it's generating basically the same thing as the naive C++ compilation was as well in its optimized way. So we can't get very angry at the JVM here for not doing it because it's doing basically what you would expect. It's doing roughly what you would expect. And me not being an ARM expert, I can't comment on the quality of either of these. Meaning, so I'm not, I don't really do much ARM work at all. So I'm not really ready to say this was great assembly or not. But what we can say is it's not doing any worse than our other compilers would, than systems programming languages were doing. Not doing any worse. Why am I unhappy? Well, I'm unhappy because, if you remember, we are calling this function a lot. Yeah. You're calling this on every line of a 1 billion line file, which means you're calling it at least 1 billion times, but if I'm not mistaken, it'll be more like 2 billion because you call it twice for most lines, right? Once for the semicolon, once for the end of line. So this is we're calling this 2 billion times. And that for loop, it's not going to go over very many characters. It's going to go over maybe 6, 7 characters, 10 sometimes. Very few, right? So now, in my head, I'm just doing the math. That loop's going to run maybe 10 times. So figure that 6, 7 instructions copied 10 times is what? 60, 70 instructions? Look at how much overhead is in this function potentially, right? There's all this other stuff. Now I'm thinking to myself, okay, I got to look through here. Maybe most of this overhead is branched around. Like maybe it rarely gets executed because, there's just a check at the top, like if JVM is in bad state, jump to this code over here. It could be that we don't have to worry too much about it. But just I'm unhappy because oh, great. Now I have to start going, is this code actually running? How much of it is running on every time? How much of it is just some random crap that's not really running and it's just checking, a quick condition or two at the top and most of the code is ignored. So there's that. But basically that's what I'm thinking on this. And so not bad JVM. I'm actually not unhappy about that. And I do think that bodes well for let's say we needed to we don't want to deal with this cruft. We could hoist this loop out into our main loop. And I think it will generate some pretty reasonable code for us. So big thumbs up for us. And I think that's something that probably we'll want to look at as we go forward a little bit, right? Obviously to simplify our lives a little, right?
Yep.
So anyway, did that all make good sense, Marco?
It did
make
make
sense. Questions?
It was good fun, and it reminded me of, the last time I started Soft Ice was a long, long time ago, displaying registers and debugging, through code. It reminded me of that. I'm super happy. It was lovely. Thank you.
Okay. And so this puts us in a great position to do a couple things. Now that you've got this, we can always go back to the disassembly when we need to think about performance stuff, which we're definitely going to want to do. But also, it gives me the opportunity to do the other thing that I really wanted. It's the reason it came up last stream, which is now we can verify that certain code is or isn't happening, right? We can put our timing code in something, disassemble that something, and verify that we're actually timing what we think we're timing, right? And that's the other big reason I wanted it. So I think this puts us in great shape for next time. And I guess what I would say is maybe you and I can talk about separately what we might want to do next time. We don't have to include that here. It can kind of be offline since we don't have any time left. But
we will do, but I think
do that.
JIT Watch also has to pop up at some point.
Okay, so maybe we'll think about it together next week. You can show JIT Watch, and then you and I will talk about what we've talked about behind the scenes about what we want to do next, and we'll start that.
Cool. Thank you, Casey, very much. And I hope
my pleasure.
Everyone had fun watching this. Let us know what you think.
Okay.
Bye-bye.
Take it easy, everyone.